This is my presentation on question 4 on the spectrophotometry and IR spectroscopy of an unknown compound by me, Arthur Reed. Question 4 says that the product of a reaction is a red solution due to compound X. It says that this is not the only product of the reaction. In order to study this reaction, different solutions of X were examined spectrophotometrically. This intro tells us that 1. A reaction has happened that has given us multiple products. 2. The compound that is making the solution red is compound X. And 3. Different concentrations are being compared by spectrophotometry. Part A of this question asks us, at what approximately wavelength would X absorb most strongly? What we know from the beginning of this question is that compound X is making the solution red, so the wavelength that X will absorb mostly strongly is the complementary color. We have a visible red, which means that green light is the light that is being absorbed, and wavelengths of light that are green are in the range 480 to 560 nanometers. So part B asks us the question, a stock solution that is 0.05 molar in X was used for the dilutions as follows. It tells us that a buffer was used to stabilize the pH. It's asking us to calculate the concentrations for X for each solution. There's 4 solutions here in this table. We can see the different volumes of X that we used, the same amount of buffer in each one, and the different volumes of water. What you immediately see is that the volumes are the same across all of these dilutions. And we also know that a dilution is taking place here, so we're going to use the equation C1V1 equals C2V2. C1V1 means the concentration and volume before the dilution takes place, and C2V2 are the concentration and volume after the dilution takes place. We're trying to find the concentration after dilution, so we rearrange to find C2. That gives us the equation C2 equals C1V1 over V2. Now, the 4 concentrations here, I show me plugging in the numbers from the table. We get the concentration of X in solution 1 comes out to 0.01 molar. In solution 2, that comes out to 0.02 molar. Solution 3 has 0.025 molar, and then 4, 0.03 molar. Part C gives us a table and says the absorbance of each solution is given in the table. If path length is 1 centimeters, calculate epsilon in meters squared mole to the minus 1. We're given a table here with the 4 solutions, which I can assume are the same 4 solutions as the previous table and previous slide, and gives us 4 different absorbances. The equation that links absorbance, concentration, path length, and epsilon is A equals epsilon LC, the Beer-Lambert law. Originally what I wanted to do was just plug in some of these numbers in the table and in the previous slide to work out epsilon. I then realized a better way of doing this would be to graph absorbance against concentration, and you can see that graph there that I made. And if we substitute the y value as A, the absorbance, and the x value as concentrations of X, C, we can compare the Beer-Lambert equation with the equation of a line, y equals mx plus c. Now this graph goes through 0. So y being A and x being c means that m, the gradient, would correspond to epsilon L. The gradient on this graph here is 22.457, so we know that epsilon L is 22.457. We're told that L, the path length, is 1 centimeters, so converting that into meters and then dividing our gradient by L, we get epsilon as 2,245.7 meters squared mole to the minus 1, and I rounded it there to 2 significant figures for the much nicer number of 2,250 meters squared moles to the minus 1. Question 4 is a multiple part question. The full question tells us that the infrared spectrum of compound X includes a strong peak at 1,640 centimeters to the -1. It says that this is due to a C double bond O in the molecule, and tells us to assume that we're using carbon-12 and oxygen-16. It's going to ask us to calculate the reduced mass, frequency in hertz, and the force constant of this bond, and finally asks us what would change, or what rather wouldn't change, if we use carbon-13 instead of carbon-12. Part DI is asking for the reduced mass in grams per mole. The reduced mass is given by the sign mu, and to find the reduced mass, you do m1 times n2 over m1 plus n2. Now, carbon and oxygen have a mass of 12.011 and 15.99 respectively. Plugging those numbers into the equation earlier gives mu as 6.86 AMU, or 1.15 times 10 to the minus 26 kilograms. To convert MU to kilograms, what I did is I times 6.86 by 1.67 times 10 to the minus 27, and I did this because kilograms make the equation in part 3 much more easy and digestible. Part DII, this is asking for the frequency of the signal in hertz. The frequency is given by that Greek V sign, and to convert from the wave number that we're given in the full question of question D, you times your frequency and wave number by the speed of light. Now the speed of light is 2.997 times 10 to the 8 meters per second. So we times the 1,640 given in the question by C, and we get the frequency in hertz as 4.92 times 10 to the 11 hertz, or seconds to the minus 1. Part DIII is a continuation of the last two questions, and it says, hence calculate the force constant of the bond. The equation we're going to use to find that force constant is that same Greek V frequency, equals 1 over 2 pi times the square root of K over mu. Mu is the reduced mass. Rearranging that equation for K gives you K equals mu, and then there's some brackets around 2 pi frequency squared. Using the value that I worked out for mu in kilograms, which you can see there, 1.15 times 10 to the minus 26, and then the value I got for frequency in hertz, seconds to the minus 1, 4.92 times 10 to the 11. I worked out the force constant of the bond to be 0.110 Newton per meter. The final part of the final question, part DIV, so D4, if one were to have done the calculations for the carbon-13, oxygen-16 bond, what would not change in the calculation? And then it excludes the value for pi and the actual equation. So firstly, what changes in the reaction? Because carbon is heavier, using carbon-13, the reduced mass increases. This means that the increased reduced mass changes the force constant of the bond, and that then increases to 0.114 newtons per meter, which isn't a very significant change. It is only off by a factor of 0.004, but it still is a change, so that is not the answer to this question. What doesn't change is the frequency of the oscillations of the bond. Those stay the same across the different isotopes that you can use. So same would be true for carbon-14 or oxygen-17. That stays constant.